Hello. Sorry, no microphone before. Welcome to another episode of Sound Talk Show. Today we are going to do geometry, calculus. If you are learning calculus, you would find it fun. So animations of mathematical curves and so geometry. Okay, let me show you some of these animations. So you see, if you have a bar and you turn it so that the end of the bar stick on the two perpendicular axes, you will trace out this curve. So this curve it traces out is called asteroid. So in mathematics, we say the envelope of this movement is an asteroid. Now, asteroid curve is very interesting. So let me show you what is asteroid curve. So this is about mathematics, geometry, and graphics programming in Wolfram language. If you have comments, questions, post it. Okay, if you are here, post it. So let me pop out the chat. So let me show you what is the asteroid curve. Asteroid curve is very interesting. In fact, we can, let me just do it interactively. So this is asteroid. So you see, when you roll a circle around a bigger circle, then you get this asteroid. The point on the rolling circle creates a trace of asteroid. So let's stop this and make it more copy new file, and let's not animate. Let's just generate a bunch of graphics and shift enter, do it. Okay, so you can see it generates a bunch of asteroid curve. So you see, this is rolling a circle that is 1/4 the radius of the bigger circle. Roll it inside the bigger circle. So I want to create more number of frames. So number of frames, let's say 40. Okay. Now, do we get more tight? 40 is too small. Let's say 80. Okay, and let's do, so we got now more dots. Fantastic. Now, let's do list animation. Okay, shift enter to evaluate it. And there it is, an animation. Fantastic. You can, so this is Wolfram language, Mathematica. You can export this into a, MP4 or any other movie format. Am I doing good? So let's see, double check, voice check, video check. Yeah, comments and questions. Hello, Huang. Hello, Souls. So this is animation. So so this curve is called asteroid. Now you see what's interesting. There are so many interesting properties about these plane curves. So you can see how this curve is generated. But now if we move a line, we move a bar so that the endpoints are fixed on the vertical axis, then it also traces out this asteroid curve. So let's slow down. What is this? Increase speed, slow speed, stop, play again. Decrease speed. Now I believe that's decrease. Yeah, slower. Oh, okay. Now it's too slow. Okay, so that's, like one of the properties of asteroid. And there's more interesting things going on. So let me show you this one. So if you have an ellipse, and if you draw all ellipses, you draw all of them so that they share the same center, and also their width and height, the sum of their width and height is the same, is a constant. So you draw all such ellipses, and also of course they have to be oriented right. So the minor axes are all the same and major axis. And then also you see the envelope is also an asteroid. So you can see this asteroid curve, we are seeing many properties of it. You can generate it by this bar. By the way, this bar, this movement is called tremor of Archimedes. TRAMMAL, tremor of Archimedes. Okay, so you are seeing this, and you are seeing the rolling circle, and then you also see the relationship to ellipse. Now, what is ellipse? Ellipse itself is very interesting. So let me show you. So you see all these are, so this is a ellipse. So this is another relation. You see, if you stop this, slow down, let's do it again. So you see, you use the tremor of Archimedes, all the same, but now you put a point on the bar and you move the bar, then that point will trace out an ellipse. Okay, so very interesting. So these are, these are about special properties of plane curves. Now, what is an ellipse? Ellipse here is another relation. So you see, ellipse can be generated also by rolling a curve inside a circle inside another circle like this. By the way, there's a toy called Spirograph for rolling circles around another circle, very popular. If you have not seen it, let me show you. Spirograph. This toy, it was very popular because when I was back in Taiwan in the 1980s, my granddad or my dad, bought me one of these. So you can actually, draw all these colorful curves by, this is a thing that has gears and wheels, and you put a pen inside it and you'll trace out all these curves. So this toy, they call this toy Spirograph, SPIRO. So they call it Spirograph, but the technical name, the mathematical name for this curve is called hypotrachoid and epotrachoid. So let me go back to show you, so you can see there it is. You see this is epotrachoid, many interesting properties, and there is hypotrachoid. Now, hypotrachoid means when you roll a circle inside another circle. So you roll a smaller circle inside a bigger circle, you get hypotrachoid. But if you roll a circle outside of a circle, you get epotrachoid. You see, very interesting. So that's a technical name for this toy Spirograph. You can buy this on Amazon. This toy is still there. So this toy is now by now 40 or 50 years old. Very popular. Okay, so you see, ellipse can also be traced out as a spirograph or epocycloid. So that's very interesting. And what about the definition of ellipse? Oh, by the way, okay, so here's another interesting property. You see, they are all related. Ellipse can also be traced out if you extend the bar, of the rolling circle. So that also generates an ellipse. Okay, but what is the definition? So ellipse can be defined in several ways. You can define it in this mechanical way, a circle inside a bigger circle of certain size. The circle needs to be certain ratio. So in this case, the smaller circle is half the radius of the bigger circle. But over here, this is also, in this case, you have to extend the bar. That also generates ellipse. But what is another definition of ellipse? The classic definition of ellipse is this. Okay, so you start with two fixed points, and you draw all dots such that the distance from one of the point to the dot to the other point is the same. So you create all dots of such property, then you get an ellipse. So this is the classic definition of ellipse. So you can see we already we have so many we have ellipse properties. You can generate it this way. By the way, you can also do this mechanically. So all you have to do is you take out a piece of board, you put you stick in two tacks, nails. Then you take a string, sewing a thread, then you tie it to the points. Then you use a pen, then you just tighten it and it'll trace out a ellipse. So very interesting. And here is another properties of ellipse. You can also generate it this way. So this is slightly more complicated than the other. So you have to form a triangle there. So yeah, so that's some of the properties of these spatial plane curves. This is another spirograph, beautiful. Okay, so yeah, so all these are done with Wolfram language, Mathematica. In fact, I wrote a package for this. I wrote it like 30 years ago. So, but I'm updating it. So I just updated it, and I will be uploading to GitHub in a few days, in 2 or 3 days, by the time you watch this video. So if you are watching this video offline, feel free to skip around. Can you draw a duck? Yes, of course you can. But I'm gonna, that's a digression. So, for example, you can, that's a digression. But basically, you want to. That's an interesting question. A lot of people ask, including me when I was learning calculus. When I first learned about plane geometry, you have coordinate x and y. So you can plot a polynomial, you can plot sine curve, all sort of curve. So the question is, can you do the reverse? So given a cartoon image, can you have an equation whose plot looks like that? Yes, that's doable, but technically, actually, if you go really deep into mathematics, technically it really depends on precisely how you define your what exactly is the drawing you want to have the equation for. Because normally when you well, let me show you. Okay, let's see. Wolfram. I have an article about it. So let's go to, if you search for XR Math blog, then go to my math pages, then search for parametric equation. Search for equation. Theories of equations. The level of math professors are not equal. Theory of equations. Okay, not there. Let's search for graph. Stereographic projection, graphics, graphing calculator. Okay, so many of you probably have seen it. So let's say duck equation. Okay, let's just go to Wolfram language. So your question is, can you plot a duck? Okay, so let's go to Wolfram Alpha. It will generate it right away. So let's see. Yeah, so you can see all these are some examples people has done. Santa-like curve. So this is drawing a Santa Claus. Okay. Santa Claus, and the equation is this. So mathematically this is not interesting. You can basically, for any drawing you can create a mathematical equation for it. But the deeper the issue is that because your drawing is not well defined. You see, in mathematics, you see many of these curves we talked about. You see, may it be the spirograph or or the ellipse, any of these curves we talked about, they are very, very precise. So, for example, this ellipse, for example, this asteroid, how do you know? Let's go here. So, so it traces out an asteroid, but every dot there is very precisely defined. So it's pinpoint down to infinite number of decimals. So if that, let's say the 100th place in a decimal is off by 1 bit, then that's not an asteroid. Okay, that's the definition of these curves. So they are extremely well defined, very precise, down to infinite precision. That's right, infinite precision. So if you are at the millionth point, you are off by 1 bit, that's technically not an asteroid. So back to your question, you kind of trolling question, Mark Jefferson. Your question is like, can you draw a duck? Okay, so we have seen a Santa Claus here, but the issue here, we do have an equation, but the issue here, your Santa Claus drawing is not well defined, not like, the math curves. So if your drawing is so well defined, so every point has infinite number of precisions, then some of the curve cannot be drawn by an equation. Okay, that's an interesting technical detail. Okay, so let's check out some fun ones. I remember there's a Batman and a bunch of others. Let's see, random DC Comics curves. So there's Batman, Superman. So what is this? This is Green Lantern. Let's see, DC Comics curve. Okay, so let's do another one. Oh, this is what? Catwoman, Prometheus. Okay, let's see. Batman curve. Batman curve. There it is. And where's the equation? Let's see. There it is. Batman curve. Sine, cosine, infinite number. Okay. So let's look at the equation. Okay. So what exactly is this? This should be, it's a parametric equation, okay? So today you have AI that just generates the equation for you. I believe this is a parametric equation. So anyway, Joman Molina, hi. I'm doing good. I'm doing pretty good. So now, we have shown some of these, animation and some mathematics about it. Very interesting. So if you want to do this, there are two interesting aspects. So one is, for example, let's say this one. This one is very easy to understand. How do you do this? You can use JavaScript, you can use Python, you can use your favorite language, okay? How do you generate animation like this? So there are two aspects. One is the mathematics of it. So in order to generate this, you have to understand exactly, where to draw the bar in every frame, where to draw it. So that part is mostly about trigonometry, okay? It's really just about trigonometry. So you have to master trigonometry or analytic geometry. So once you know, you can draw this, because, for example, if you want to draw this, what you have to know is, for every frame, you have to know where to draw this small circle and where do you put that bar. So that is mostly trigonometry. You need to be a master of trigonometry, very basic. So that's one aspect, the math aspect of it. The other aspect is the technology, the programming language. For example, if you want to do this in Mathematica Wolfram language, you have to know Wolfram language. So let me show you the code. Desktop, so Wolfram language packages. So I wrote this like 30 years ago, and recently I just updated today. I updated, a few weeks ago. So here is the code. So first of all, here all these are documentation. Can you see it? Yes. So these are documentations. Then let's go to the code. So for example, this is an auxiliary function, and this part is a general function for doing any polar equation. So let me show you some more of it, some more advanced. So for example, all these animations you have seen so far, they are specific. For example, this one is for ellipse, and this one is also for ellipse, but very specific. But you can also create an animation that do like you give an equation, parametric equation, it'll generate an animation illustrating that. So let me go to one of them, and so you can see. Yeah, so let me show you another specific one about sine curve. Okay, this one, by the way, this one is also interesting. This curve is the red line, the red dots is called quadratrix of Hippias. This curve is about 2,000 or 3,000 years old. Okay, 2,000 years old. Asian curve, this red line. And from this animation, you can see how is it generated, how is it defined. You have a bar moving from bottom to top in a constant speed. Then you have another bar that rotates in a constant speed. So when these two bars move, they intersect. All the points of their intersection is the quadratrix of Hippias. Okay, and there's an equation for it. You can plot it. But anyway, so the purpose of this animation is to visualization of geometry, to visually show, all these properties. So you can look at it and you understand how is it defined. So let me show you some more specific, interesting ones. Then we'll show a general purpose one. So here is how sine is defined. Sine, cosine, tangent, cotangent. All of them can be defined by a single function, sine. And how is sine defined? You can define sine mechanically like this. Okay, so you have a circle. You roll. So you have a bar centered in the circle. You just roll it in a constant speed. That's important. Constant speed. Then you have another bar that traces the height of that rotating bar. That's how you get sine. That's basically how sine is defined. So that is why sometimes the sine function is called circular function, because essentially it's defined based on a circle. And sine function is the most, you could say sine function is the most important function in mathematics, most fundamental, back to like 3,000 years old. Trigonometry is the most important, and all over physics. So sine function, in other words, you can say sine function represents pi. Okay, represent the ratio of a diameter of a circle to the circumference. Basically, sine is pi. Okay, that's sine function. And here is another interesting animation. This curve, so you can see the envelope, all this line art formed a curve. This one, kind of bell shaped, that's called tractrix. Okay, tractrix. And you can see this in real life. That is, when you have a bicycle, let's say you ride a bicycle on slightly muddy road. So usually when you ride a bicycle, you go straight, right? Now, when you turn a wheel, when you turn the wheel, then you maintain that that angle, then the 2 points of your bicycle's wheel will trace out this curve. So it's like dragging a line. So you can see we have a fixed bar, the red bar here. We just drag it and it will trace out this curve. So it will also trace out by your bicycle. So this curve is called tractrix. Very interesting. And then, okay, so let's go to the more generalized advanced. So here is a function that does generalized polar equations. So for example, we are given an equation t and cosine t. So x equals to t, y equals to cosine t. I mean, theta equals to t, which is the angle, and the distance is cosine t. So you can see it's easier when you just see it. So you see it generates, so this is a polar equation. You can give any equation to it and it will generate an animation. Okay, and here is another example. This another polar equation example. So that's mathematics, and here is another example. So here, what's interesting is that if you want to write this program, you can of course write it in JavaScript, in Python, in whatever language. What you need to know, I mean, this is a generalized animation generator, so you can give any polar equation, parametric polar equation, and it will create this animation. So you have to know, trigonometry and analytic geometry so that for each frame, you know what to draw, which line and which dots. And let me show you last one is a very interesting and more advanced for derivative. Derivative, which is the fundamental part of calculus, the most fundamental, can also be generated by mechanical means. You see, so far all the things we've seen is almost all mechanical. That is, you can create linkages, that's what's called linkages. Let me show you. So linkages is a very important field in robotics. Okay, so for example, all these are linkages, and especially in robotics, because in robotics you have arms that needs to move in a certain way. You cannot move freely, but usually a motor just move around, round and round, or back and forth. So, but you want to make it so that, for example, a robotic dog, the legs movement, it must be in a certain way. So all these are done by what's called linkages. So far, all these animations we've seen, they are linkages. Many of them are linkages, but basically they are all mechanical means of doing things. So, for example, you have this thing that controls the, for example, the camera shutter, things like that. And here is a bicycle linkage. Can you see it? Okay, so back to here. So I was saying the derivative actually can also be generated mechanically. So let me show it here, there. Let's go slowly, okay? Slow. Stop, play. Slow. Okay, and here is another derivative. This is a derivative of a parabola. X equals to x squared, y equals to x squared. Very simple. So the derivative of a parabola is a line. and here is how it works mechanically. Okay, so is that interesting? Maybe that's it for today. So let me talk about how do you, the code. Okay, so for example, let's say the first one. This tremor of Archimedes, okay, how is this done? So let's look at the code for this one. So I have Concord, let's see, search for asteroid, okay, search for asteroid, there it is, asteroid generator. So the code is here. Yeah, actually it's not too big. It's basically just these lines. Okay, it's just these lines. So what I'm doing is that for each frame you want to draw the line, the red line, the axis so basically for each frame you want to draw the red line, the bar, the fixed bar, and the line of its previous position. And you can see this part is a line. You see, line starting position is cosine something 0, and end position is 0 sine. So so how do you know sine cosine? Well, that's trigonometry. You have to figure it out. So basically the essence is just simply this line. So this animation, the essence of this animation is simply just these 2 points, beginning position of the bar and end position of the bar, cosine 0 and 0 sine. And the rest is just Wolfram language graphics. And you can do this in JavaScript, of course. JavaScript is very suitable for the web. So what else I want to, let me go back to so maybe that's it for today. What else we want to, let me see. So show the animations, explain a bit about each, show Wolfram language tutorial site. Yeah, okay, so if you search for Wolfram language tutorial on xali.info, so I have all the tutorials for programmers on Wolfram language. You can download it free, over here. And then there's I updated a new section on programming graphics. So all these are about programming graphics. So you just go down and advanced symbol principles graphics programming there. So so you can learn about that graphics programming. So what else? Demo the manipulate. Okay, so another one. So here is about one interesting feature of Wolfram language. Let's say plot. Okay, let's say you want to plot sine x. Okay, and let's say x from 0 to 6. Okay, that's sine. Now what if you want to sine x times 2? Okay, what does it look like? So let's do it here. Sine x times 2 inside. Okay, so you can see it kind of compress them horizontally. Now what about 3? You see, it's more compressed. So you can create an animation. So how you do that is you just call manipulate, manipulate. Okay, then just exactly like before. No, not that. Yeah. So sine x times 3. x 0 to 6, but here instead of 3 we say t. Okay, so t is a new variable. Then over here we say t goes from, let's say, 1 to 3. Okay, do it. Shift enter. So now you got this slider. You can see as t increases how it changes the curve. So can you show the value? There it is. Then also you can do it by animation. And let's cycle it. You see, that's a fantastic, the most wonderful feature. So this feature allows you to see the effect of parameters of functions or equations to the functions graph, so you can easily visualize it. Now let's do some fancy one. Okay, let's say plot 3D sine x times y, then x from 0 to 7, y from 0 to 7. Okay, what we get? Okay, now we want to, okay, let's plot another one. Let's say sine times cosine y. What do we get? Okay, that's what I'm looking for. Now, what if you add a number here, so, and see how it changes the graph? So let's do that. Not here. Manipulate. Okay, something like before. Then here we say t from 0 to 3. Okay, and let's just say t. Okay, do it. Okay, we got let's say animation. Do it. Oh, it doesn't. Oh, okay, it kind of shrinks the parameters. So let's change something here. Plot range. Let's say 0 to 7, x for x, 0 to 7, 7 for y, and z, let's say -3 to 3. Do it. Okay, let's see what happens. There it is. Fantastic. So you can see the effect of the variable t here to the, but this one is not interesting. The more interesting, let's make the wave move. So in order to do that, you want to put the t inside. So let's copy the previous input and put the t inside here, t. Shift enter. There it is. Show. Let's see how it changes. Okay, it's getting more interesting. And what about, let's put a t here too. Wow, that's more interesting. Okay, now the resolution is not so good, so let's make the resolution sharp. So what we want to do is we plot range, we add option, plot points, 50. Shift enter. Fantastic. Okay, they are, it's not actually moving, but it's actually becoming smaller. So, but what we want is moving, like the wave. So, what we have to do is instead of multiply by t, we say plus t, okay? Actually, I think we can put the t outside. Yeah, I think that's probably, yeah, there it is. It's moving, but yeah, you should actually just put the t outside. So here plus t. Oh no, it's not. Yeah, now it's just move up down. Yeah, it should be inside. But anyway, so this manipulate is a very useful, extremely useful function in Wolfram language. Okay, I think that's it for today. How to create animation? So we haven't get into programming Wolfram language graphics. Let's do that another day. Yeah, so we just introduced some interesting mathematics today. I know a little about asymptote and metapost. Okay, I don't know what's a metapost. Okay, that's it for today. Thank you guys for watching. Now, for those of you watching Xa Talk Show is a variety nerd show. I talk about a bunch of very interesting nerd topics. Mathematics, programming, geometry, keyboards, and mouse. And now I bought a new camera. So, do they have a picture? No, they don't have a good picture. But this camera is called Mocos. So, this camera will allow me to give you great close-up of keyboard. But right now I'm using Logitech, cheap Logitech webcam, so you don't see sharp pictures. And also, let me mention again, this is Svalbard, Svalboard. I promised to use and demo, and so I have a review on my website, but it's very short, 20 minutes or so. But I will be using it, until I will be learning it and show you guys. So I want to mention that until actually I start to use it. Okay, that's it for today. Thank you guys for watching. If you like my stuff, you can just go to xali.info. xali.info, enter, and that's my website. And you go down down the rabbit hole. Then you can Patreon me, Amazon gift card me, or PayPal me. Okay, pay me, because if you like my stuff, that's how things gets going. Thank you guys. Bye guys. Shut down in 1 minute. You see, I'm using this mouse, this trackball I reviewed about 4 days ago on my YouTube. Fantastic.